Let's talk about the concept of an unfair game. So these ideas that we're learning about are actually commonly used in casinos and a lot of game design where you're charged a certain amount to play and then you have these expected winnings. That amount to play is typically strategically chosen so that in the long run they're making a profit from the game. So let's talk about applying this to a dice game. And this is a game just made up. This isn't a real game, but a lot of these ideas will apply to actual games that you would see out in the real world. So we're going to roll a die. And if it comes up a 6, you win $100. If not, you get to roll a second time. If you get a 6 on the second time, you win $50. If not, then you lose. So, first thing we're going to start with is creating a probability distribution for the amount you win. What can sometimes be helpful is just writing off to the side the possible outcomes, or you can even write it by the table. So to start our table, we'll have our x values and the probabilities. In this case, it gives you a guide for what to have x represent. We want x to represent the amount that you're going to win. So for x is going to be coming from the amount of money that we win. So in terms of our possible outcomes, it's describing 3 cases. The first case is that we roll a 6. The second case would be that we roll not 6, and then a 6. And the last case would be rolling not a 6, and then not a 6 again. So these are our 3 cases. If we roll a 6 on the first roll, we get $100. So that would be the amount that we'd win. If not, we get to roll a second time. So if you get 6 on the second time, you win $50. And then our last case is that we lose, which means we win $0. Now what we're going to do here is figure out the probabilities. In fact, let me just kind of emphasize, here's our actual probability distribution table. I just have work kind of going on outside of that. So this first case here, to find the probability, it's just what's the probability of rolling a 6, which has a 1 out of 6 chance of occurring. So you can either use the fraction or you can use the decimals. If you want to use rounded to 4 decimal places, you can do that. Or if you want to type in fractions, that's fine too. I'll go ahead and use the decimal form, but either way it should give you just about the same answer. All right, for our second case, we want to see the probability of not a 6 and then a 6. So and then probabilities, so from a few weeks ago, talking about probability, when we work with and then, it's multiplication. And we just need to make sure we have independence here, which rolling a die is independent. Seeing one outcome isn't going to change the probability of a second outcome. So probability of not rolling a 6, well, there are 5 options out of the 6 that are not rolling a 6, and then multiply by probability of rolling a 6, which is a 1 out of 6 chance. So that multiplication part will be our probability, which will be a 0.1389. And then our last one, which is the probability of rolling not a 6 and then not a 6 again. So again, and then we'll bring through that multiplication. So we'll have probability of rolling not a 6, so 5 out of 6 chance, times probability of not rolling a 6, 5 out of 6 chance. So multiplying those for a 0.6944. When you have to make a probability distribution table for yourself, and especially using probability rules to fill in those values, just do a double check that the probabilities add up to 1. That's a good way to make sure that you calculated probabilities correctly, that you've covered all of the possible cases. It's just a quick way to make sure you're on the right track. All right, expected amount you win. So expected value, we're going to go through and take each x value times its probability. So 50 times the 0.1389, and then the 0 times 0.6944. So this will be expected winnings of $23.62 rounded up. I'm going to make a sentence after we make standard deviation to just tie it all together instead of writing separate sentences. All right, standard deviation. So we need to take those squared deviations times their probabilities. So what we're going to do is take 100 minus, and actually, sorry, since we're using our expected value down here, I know I rounded. When you have your expected value, this rounds to 3 decimal places just automatically, but use our rounding rule of 4 decimal places when you can, because in our standard deviation, we're going to keep using that expected value over and over with our calculations. And if we round at the beginning here, it'll throw off our solution. So I'm going to keep that exact there, and then I'll round in the sentence. So 23.615 squared times its probability of 0.1667, and then 50 minus the expected value squared times its probability of 0.1389, and 0 minus 23.615 squared times 0.6944. And then what we'll do is add up those values to get our variance, which in the calculator that should give you a 1,456.5818. And then you'll want to take the square root to get the standard deviation, which will be a 38.1652. So what we're seeing here is that, let's see, we're saying we're playing the game. So what's the expected amount you'll win? I expect to win $23.62, and on average this will deviate by $38.17. So with this, we're saying when we play this game, we expect to win about $24, and on average that'll deviate by $38. Now this case where the standard deviation is larger than the mean, it just means that 0 is a very high likelihood, which we can see from our table itself. It's that on average we expect to kind of land here, and then in terms of deviation, it does go into the negative region, and it's just emphasizing that 0 is a high likelihood here. Now, a common question at this point is saying, like, I expect to win $23.62 from this game. I feel like it doesn't make sense because, well, you can only win $150 or $0. But this is the idea of playing over a long period of time. So this is where, like, the casinos or game designers would come in with the idea of, okay, if people are playing this long run for a long period of time, how much do we expect each of them to walk away with? And so it would average out to this amount of $23.62. So that's the concept of expected value here. It isn't just what is expected in a single game of play. It's like long run, how is this game operating in terms of expected payout or expected winnings? So this is our earnings. We expect to earn this $23.62 whenever we play. What we're going to add in now is a cost of play. Should you play this game if it costs $25? Why or why not? So what we want to use is what we talked about in the last video of taking your earnings minus cost. So what we do is we'd be earning $23.62 on average, but what if we took out a cost of 25? And this would come out to a negative 1.38, which suggests a loss. So we would not want to play this game because the cost of the game is higher than the average earnings. So we have there is an expected loss of $1.38. Just to tie in with a MyOpen Math question that could come up here, if they prompt you to say like how much is the profit, if you're coming through with a loss, you would just type in the negative number. So you go negative 1.38. But in terms of writing a sentence, if you say it's a loss, then you can portray it as a positive number because loss brings through that idea of negative. So this is what game designers and casinos use, is that on average, what do they expect people to walk away with? And then they bump up the cost, and they tend to be pretty strategic with how they choose the cost of the game. They don't want to be super obvious that they're making money with it. But with a game design like this, where you could walk away with 0, 50, or 100, 25 isn't too bad of putting into play when you could double or quadruple your amount that you're winning, and then there is this chance of walking away with nothing. But it seems like it can feel like a higher likelihood of winning something when actually it's not, based on the design of the game and the fact that they've set the price in a way that in the long run they're making money. Even if they do have someone win this $100 and have this big payout, they've kind of made up for it with how much they're charging everyone else to play, so that they're making a profit and the people that play on average are coming up with a loss. So this would be the idea of an unfair game. It's designed in a way with a cost that's higher than the earnings that are expected. So to make an unfair game, all you'd have to do is set a cost higher than your earnings. If we wanted to make the game fair, you just need to design it so that the earnings are the same as the cost. So we would just need a cost of $23.62. If we set up that game, then we would expect to completely break even in terms of people paying to play. There we go. They'll break even in terms of people paying to play and handing out money for those that win. So this is some game design in here working with our expected value.